Hello, everyone, and thanks for joining our second webinar of 2023 on wellbore remediation. Uh, Starting in 2021 and into 2022, Innotek conducted a series of webinars on new technology for wellbore remediation and plug-in abandonment. And as this is a ever-changing landscape with new technologies being developed and tested, we wanted to continue this on in 2023. So today we have four speakers to introduce their technologies for wellbore remediation. I will start with a short introduction just to introduce the topic and some of the motivations around these new technologies. And then we will have about 20 minutes per speaker with 10 minutes of Q&A following their presentation. On your screen, you should see a chat area where you can enter your question as text, and I will read the questions aloud to the speakers. At the end of the webinar, after all four speakers have presented, we will have time for some additional Q&A if there are more questions and you come up with something else you'd like to ask. And if there are no more questions, we'll end the webinar as it kind of naturally comes to an end. Next slide, please. So just to set the stage with a problem statement, wellbore leakage affects all types and ages of wells worldwide. So it's a very wide-ranging problem where there's opportunities for collaboration and sharing of knowledge. We have estimated that there may be 50,000 wells leaking methane in Canada. So admittedly, this data is not very good. There are known leaking wells. I believe the current number is about 22,000 leaking wells reported in Alberta. But in all of Canada, and including those wells that are leaking but not known to be leaking, it could be upwards of 50,000. As well, there are about 250,000 wells in Canada that will need to be abandoned over the coming decades as wells finish their useful lifespan and new wells are drilled. In terms of the leak rates, there are a very wide range from a few bubbles to several hundred cubic meters per day. But ultimately, at the end of the wellbore's life, the regulations state that zero leakage is required. So that is our target for sealing these wells. In terms of leakage path, I think they could be divided into two different categories. So one is through existing casing plugs or new casing plugs that will be required for abandonment, as shown in the often referenced diagram there. The other is leakage through the cemented casing annulus, where numerous cement defects and flow paths can cause leakage either to the atmosphere or uphole zones, including aquifers. So the premise of some of our work and the interest in the topics being presented today is that alternative materials to Portland cement may offer improved performance for plugging and remediating these types of wellbore leaks. Next slide, please. So what makes these alternative barrier materials better? Well, they have some desirable characteristics, and not all materials have all of these, but these are some of the things that we're looking for. The first is a solids-free composition, or fluid properties allow them to be placed into very small flow pathways where gas can escape to surface or uphole zones. Superior mechanical properties such as strength and flexibility, as well as bond to casing. Environmental resistance, so chemical and corrosion, as well as resistance to temperatures, and the general downhole environment, which should lead to improved longevity. These materials are intended to be permanent and last for forever, I guess, would be the goal. A curing behavior, that is advantageous. So you often hear about right angle set, but a controllable curing behavior in various downhole environments is very beneficial. As well, some of these materials offer very low permeability, essentially zero in some cases. Some of them might expand upon setting compared to Portland cement, which generally shrinks. Rigless deployment means that they can be placed in the well without a service or drilling rig. And ideally, they could be placed without pulling the tubing or other downhole equipment, such as instrumentation lines and so forth. That will greatly decrease the costs for equipment and time in the field. As well, some materials will have a lower CO2 emission during manufacturing compared to Portland cement. So depending on the quantity of material provided, this may be significant. So in our investigation of these materials and in some of our work we're doing, we're not saying that Portland cement will be replaced. Portland cement is a good material, and it has applications where it's the right choice for various reasons. But the premise is that there are complex downhole situations that need to be addressed. And in some of those situations, these alternative barriers can provide better performance. However, there's not going to be one technology or material that solves all the problems. So we need a range of suitable technologies to choose from. Next slide. So with that, we have 4 such companies and speakers today presenting their materials and technologies. So I'll introduce them all now, and then, as I said, we'll have each presentation followed by Q&A. So our first speaker today will be Kyle Roebuck, Marketing Manager at BASF. He will be followed by Travis Rudy, the Technical Sales Manager at Interwell. Then Ryan Wilton, Senior Reservoir Engineer and Technical Specialist at SNF. And Mike McDonald, Chemist and Technical Lead at PQ Corporation. So with that, we can go to the next slide, and I'll pass the microphone over to Kyle.
Hello, everyone. Thank you for your time today. As Jonathan mentioned, my name is Kyle Roebuck, and I am the marketing manager for BASF's construction polyurethane products. I also have with me today Pat Webster, who is our technical service lead and who has developed the product that we're going to be talking about today. I'll start off by saying that polyurethane is more on the emerging technology end of the spectrum for well closure. We have done some laboratory testing ourselves as well as with our industry partners. However, any of the work that we've done with our partners is protected by a non-disclosure agreement, and we can't share any of that information publicly. But this is why we're really excited about Initech's program to test and validate new technologies for well closure, and really hope we can work together to further explore polyurethanes in this application. Next slide, please. For the agenda, just briefly, we're going to talk about BASF, who we are. We're going to explain, for those that don't know, what a polyurethane is. And then we'll talk about some relevant applications that led us to start looking at well closure. And then we'll share some properties of our product, as well as benefits and limitations, and finally our path forward in Q&A. Next slide. BASF is the world's largest chemical company. We're based in Ludwigshafen, Germany, but we operate in over 60 countries. BASF has 11 divisions. The division we represent today is called Performance Materials. And basically, we make polyurethanes for a variety of applications. Our division, the construction division, focuses on applications such as spray foam insulation, polyurethane for architectural panels and walk-in coolers, pipe insulation, as well as adhesives and binders. We also produce elastomeric coatings and specific onshore and offshore oil and gas products. Next slide, please. So for those that don't know, a polyurethane is a polymer that is produced by the reaction of a polyol and an isocyanate. A polyurethane system is custom tailored to deliver specific properties, for instance, compressive strength, insulating value, expansion rate, etc. These custom systems are designed in two parts. The resin component contains the polyols, the catalyst, surfactants, blowing agents. They give the finished polyurethane the desired properties. And then secondly, the isocyanate. You can see below in these time-step photos of a polyurethane reaction where the resin and iso are poured out of those beakers into a cup. They're mixed, and then the reaction starts, with the polyurethane beginning to foam and expand until the reaction is complete. All right, next slide, please. So for over 40 years, BASF has been supplying polyurethanes into the oil and gas market. Here's some examples of our applications. On the top left, GSPU, or glass syntactic polyurethane, is an insulation system for deep water applications used for thermal management of subsea flow lines. GSP is reaction injected molded, where the components are injected into a steel mold that surrounds the pipe's outer surface. The product also contains glass microspheres that resist heat flow and the extreme forces found at subsea depths. You can see on the picture that's a barge loaded with GSPU coated pipe ready for deployment. Top middle, we also provide polyurethane products, or I'm sorry, top or bottom left, to protect anode tapers during deployment. And we also have several products for insulating onshore piping, as well as elastomeric coatings to protect the polyurethane. And then in the bottom middle, we also have polyurethane for offshore shims. The two photos on the right are more on the installation side for pipelines. We sell polyurethane products as erosion barriers, either breakers or pillows, to help stabilize underground pipelines and prevent soil erosion. If you can look in that upper right photo, that box truck there is an example of the size of rig that was used to spray those breakers. So pretty compact and small footprint, improving flexibility to a variety of job sites. Next slide, please. So a newer application for us is void closure. And we developed these products that can be used to completely fill underground tunnels, for example. So on the two pictures on the left, you can see an underground utility tunnel. It's over 100 years old. It was abandoned, and there's risk of cave-in, damage, etc. So a utility approached us about filling it with polyurethane foam. You can see the end result at the second photo there. We've also taken it a step further and looked at pipeline closure as well. There's an example photo of an underground pipeline, a couple hundred feet underground, that we were able to close with polyurethane foam as well. So after we launched these products, we started getting some inquiries asking if we could use polyurethane to plug abandoned oil and gas wells. And it's not something that we had thought of, but we said, hey, we don't see why not, but let us take a closer look. And that leads me back to the industry partners I mentioned previously. We've been working with them closely and results are promising, but again, our NDA prevents me from sharing that data. But here's what I can share. Next slide, please. So a broad overview, here are the physical properties of the current product that we've developed. The physical properties shown here were measured in what we call a free rise or hand mixed cup in the lab. In the field with proper mixing and some packing pressure or back pressure, the properties will definitely be different. Strength will be higher, the compressive strength, mechanical strength will be higher. And it just really depends, on the application. But right now, density is around six pounds per cubic foot, compressive strength 96 psi, tensile strength 112. Elongation 10%, so definitely some flexibility, some ability to expand and contract, create a good seal. And again, these are all properties that we can modify based on the chemistry. And water absorption is low, helping to make sure that the product doesn't get waterlogged in wet applications. Next slide, please. So the next question we asked is, will the foam prevent methane leakage? Obviously, as Jonathan mentioned, abandoned wells leaking methane into the atmosphere is not helpful for our climate change goals. So we set up a simple test rig where we installed some polyurethane into a pipe to look for any methane permeation through the polyurethane. We saw no permeation up to 80 psi, which was the limit of the rig that we had in the lab, but some subsequent testing has shown success at much higher pressures as well. Next slide, please. We also wanted to be responsible and make sure our polyurethane wouldn't have any issues with groundwater contamination. So we sent a sample of our product to be tested against NSF standard for drinking water components. You can see the summary here, but basically we passed, ensuring that we would not be introducing any contamination into nearby groundwater. Okay, next slide, please. So overall, benefits and limitations.
Sorry to interrupt you, Kyle. Hope you can hear me, but we cannot hear you any longer. Pat, are you able to cover this slide while Kyle gets back online?
Yeah, no problem. So as he was starting to say, the benefits of the polyurethane are listed here. So the materials have a low viscosity, which allows them to flow quite long distances. There's also a fairly long gel time. This can be adjusted, the gel time and viscosity, and most anything listed here can really be adjusted to your specific job. But the gel time of the system we have currently is about 15 minutes. So this also helps the material to flow, hundreds of feet, maybe even further. I mean, we've only tested, as Kyle mentioned, in the chemical pipelines that we had sealed. There's an expansion rate of about 10 times in the current formulation. So one drum set will fill up to 150 cubic feet. And the polyurethane expands during reaction to fill cracks and voids completely. And as you saw in that earlier photograph, the equipment can fit in a box truck. There's also a photo here of the rig we used to fill the chemical pipelines. So you can see it's fairly compact. It can be towed to a job site very easily. Limitations of polyurethane, because it's an organic material, The temperature limit is about 85 degrees Celsius without any specialized modifications to the basic chemistry. And then some of the key design criteria would be compressive strength, design pressure, and adhesion to the pipe. There can be a trade-off in some of the properties if the formulation is modified. For example, reducing the density to allow less material will result in lower compressive strength, meaning the PU may not withstand the pressure of some of the gases being emitted. And other considerations would be like, are there bends in the pipeline? Bends would increase the allowable design pressure by providing physical blockage. In addition, any chemical or mechanical bonding of the urethane to the ID of the steel pipe. I believe that's it. Can we go to the next slide? So yeah, basically that's our material in a nutshell. We've been doing this for quite a long time. So we can modify the chemistry if there's something that you would like specifically. But again, there will be limitations, especially I would say on the temperature side. Pressure, back pressure, and so forth. I think we can meet the needs of any application in well closure. So with that, I guess we can open it up to questions, and hopefully Kyle is back online.
Kyle, can you hear us? Are you there?
Okay, well,
You might
if there are
be
any
on your
questions.
own. Sure. Yep. There are a few questions coming in. So
Okay.
The first is from Chris Morgan. So it looks a lot different than your construction work in an oil field environment, I guess, or wellbore, with pressure control, BOPs, tubing, cement head. How would you be able to pump this from surface downhole? And I guess in the case of remediation into perforations or for abandonment into the casing. And I guess I might expand on that a little bit. Do you have kind of a concept for how this will be deployed for abandonment? For instance, would casing have to be milled out? How long of a barrier would be required? Would you inject from surface or inject
It
down tubing or
it it
those
would
sorts of?
it will depend on the application. We've actually been discussing this with one of our applicators. We have a company the one that did the work with us in the chemical pipeline. What we would foresee in the field actually would be to have the lines actually go down into the wellbore and have some sort of static mixer at the bottom. There could be a mechanical mixing as well, but I think the most cost effective would be to have a static mixer at the end of the tube, and then we could retract it as the urethane is filling into the annulus.
Great.
Yep.
Yep, this is good. We have a question from Trevor Olescu. Have you tested this to simulate wells with a history of H2S or CO2? And how does it perform? Any adverse reactions in kind of those harsh chemical environments?
Well, that's part of the item that was covered in the NDA. Our industry partner has done some testing on some of the, let's say, materials that you would find downhole, but I'm not at liberty to really discuss those results. There will be some chemical resistance tests though that we can do like H2S on our own. And if you would have a list of chemicals that you would like us to try, the resistance testing to, we could certainly look at that in our facility.
Sounds good. Is the product delivered with components mixed, or is there any chance for excess, I can't say this word, isocyanate,
Yes.
isocyanate that might be concerned with groundwater?
Well, the materials are not mixed prior to injection in the ground, so that you would have the resin, which is the blend of polyol, catalyst, and so forth that Kyle had mentioned, and then the isocyanate is separate. The isocyanate does react with moisture, so there would be, if there is any spill on the surface, it would react to form urea, which can be dug out. But in what we've seen with proper handling, though, that's not been an issue. Our customers have not had any spills that I know of, but of course, there's always a first time, and not everybody's the same. So, yes, there is a risk, but I think the risk is low with proper handling. But also the isocyanate will react with the moisture and form urea, which is non-hazardous.
Okay, that makes sense. One from Catch a Student here. How flexible are you in the design of the expansion factor?
Very flexible. It can go from elastomeric, which with this material, I would say a full elastomer would be, say, like 1.1 specific gravity. And we're currently at, as it was, about 6-pound free rise PCF. We could go even lower, but once you start getting lower, then you start getting a trade-off on the mechanical properties, and that's where the compressive strength will come into play. And we thought that we're right now probably about the lowest free rise density that we would like to go. But again, we take direction from our customers. So if somebody says no, we can go lower, then yes, we can certainly modify it and provide a lower free rise density if you're concerned about material usage.
Okay. We have a question here from Fred Wasmith. Can the foam penetrate into small leak pathways? So maybe to expand on that, for my interest, say like perforation tunnels or even casing leaks. Have you done any testing in that area?
We have not, but as we indicated, the material is fairly low viscosity. So there would be a chance for the material to flow somewhere, maybe where it's not desired. But again, it's reacting as it's going on. So the material does build viscosity as the reaction continues, and it becomes fully set in about 15 minutes. So it's going to stop flowing in 15 minutes, if that's what the question is. But it will slow down. As I say, the viscosity is constantly increasing throughout the reaction.
Okay. Sorry, I'm just reading through here. I had a question. I imagine the foam is fairly insulating, like thermally. Have you looked at placing it sort of outside tubulars or casing for that purpose, either in, well, it depends on maybe the type of thermal well, or wells through permafrost, or anywhere you really want to control the temperature of that fluid stream?
If you're talking about, yeah, encasing the outside, that's certainly an option. I mean, that's what we do with our business. For example, you saw the GSPU pipes. We also do a lot of rigid foam for district heating and cooling. I mean, that's where our core business was before entering this field. It's for, basically insulating the pipes for application or deployment in the field.
Yeah, I was just kind of thinking of an area where, vacuum insulated tubing might be desired, but this could be another option.
Okay. Yeah, I don't know. The vacuum insulated application we haven't looked at, but again, conceptually, I don't see why not.
All right. I believe that's all of our questions. So unless anything comes in the next 10 seconds,
Okay.
I'd like to thank you for finishing up that presentation and
Well,
dealing with the
well, yeah, I'm glad
challenges.
I joined, Kyle, after all.
Yeah. No, that was very good. Very interesting to hear. Thank you.
Thank you.
So with that, we can move on to our second presentation by Travis Rudy at Interwell. Travis, if
Morning,
you're there.
everyone.
Yeah.
You betcha. First off, thank you to Innotech Alberta for the invitation to speak today. As mentioned, my name is Travis Rudy, and I'm the Technical Sales Manager in Canada for Rock Solid and Interwell. And lastly, on behalf of Interwell and Rock Solid, thank you for joining us for this presentation on Rock Solid, a permanent P&A barrier solution. So next slide, please. Just a quick disclaimer and legal note, we do have patent or patent pending information that will be described in summary form within this presentation. So we ask nobody distribute this to colleagues or take pictures, stills, things of that nature. If you wish for more information, we'll be happy to set up a meeting and provide you more specific information that you can distribute accordingly. Next slide, please. So a quick note on Interwell. Interwell, for those of you who are not familiar with us, is a global service company in the oil and gas industry with operations on every major continent where oil and gas operations in fact occur. We do have products and technologies for each phase of a well's life, from completion to intervention, and then lastly in the P&A cycle. Rock Solid specifically was created by Interwell by pioneering the use of thermite to deliver the reinstatement of caprock integrity. Created to safely and efficiently P&A a deep reservoir in an offshore environment. We're headquartered in Norway. You can understand why that would be a concern that was brought to us. Today, however, we utilize Rock Solid to eliminate surface casing vent flow and sustain casing pressure in wellbores in Canada and in the United States. We are a rigless deployment deployed off of wireline, E-line specifically, making it a rigless deployment system and reducing overall cost environmental concerns to our customers. We do have technology and R&D advancements constantly ongoing that continue to move us toward our initial objective of that offshore deployment. Next slide, please. So to understand how this is all possible, we need to talk about the uniqueness of Interwell's bismuth barrier. In comparison to other companies where transported bismuth metal is transported down the wellbore to this desired setting depth, where they continue to melt that bismuth metal at temperatures of a couple hundred degrees to attempt and intersect and remediate the problem. Interwell's Rock Solid technology, however, is very different. We utilize thermite reaction to produce the bismuth alloy as a reaction product. This exothermic reaction can create vast amounts of heat. The reaction temperature reaches plus or minus 3,500 degrees Celsius. More than enough heat to remove the surrounding wellbore elements at the setting depth. So the next slide here will show kind of an image of our product. The barrier is created in the single run operation, as I mentioned earlier. Prior to that run, a drift run is conducted to ensure we can reach deployment depth, as well as a bridge plug is set at the desired setting depth. So on the left-hand side is a digitized still image of what we'll see later on in a quick animation of the barrier phases. There are 3 phases that make up our barrier. From the bottom moving upward, the bottom being the seal phase, consisting of bismuth alloy that we create as a result of our reaction. It provides a seal across the full wellbore cross section, and again makes up the bottom of the barrier. The middle portion of the barrier is the sequester. So it's the melted casing and metals that form the center portion. They are in fact encapsulated by the bismuth alloy sealing material. And lastly, the upper portion of the barrier is the support section, which is oxide, artificial rock, if you will, which provides the anchor support and mechanical support, holds that barrier in place during the reaction process. During deployment of Rock Solid, once it's setting depth, the reaction melting process begins. Once the melt is solidified, the resulting barrier is shown, slide previous. The resulting barrier is shown in the picture in the middle of the screen. So that gray glob, if you will, again, is another still image from the animation. To the right of that is an actual sample of a full-scale test that's been cut open. So we're looking at 180 degrees of that barrier itself. The picture on the right-hand side just kind of indicates what portion or what is what within that barrier as it relates. So from the bottom, again, you have a bridge plug. It's right at the very bottom of that screen. Then you've got the bismuth alloy, which is the grayish silvery color. The yellow orange color above that is the casing steel sequester material, and then the oxide rock anchors it up there. We do have, as a result of our reaction, some spray, if you will, that moves up into the casing itself. At the top part of that picture, you can see where the casing is still in play, and the oxide is actually filling inside of that casing as well. Next slide, please. So now that we've kind of described really quickly what the product is and what it looks like, let's discuss quickly how we kind of came to be. So the evolution of Rock Solid. It was started as a radical concept in 2012. It's over the last 10 plus years has matured into a new barrier technology that has been accepted by regulators where it is deployed. So in Alberta, it is accepted as a non-routine abandonment technology by the AER. It has been deployed in British Columbia, accepted by the BCER, as well as in Saskatchewan and accepted by the government of Saskatchewan. A very important part of this journey has been following DNV's recommended practice for technology qualification. So it's a process we started in 2013. For those of you who are not familiar with DNV, it's Det Norsk Veritas. They are one of the world's leading certification bodies. They are involved in technology process qualification in a very wide range from the automation industry, to the oil and gas industry. Next slide, please. So during this technology qualification process, we fundamentally, the process itself is fundamentally based on a threat assessment of potential failure modes of the entire operational life cycle. For all of the identified threats, we provide sufficient evidence to demonstrate that the threats were understood and risks associated with those threats were acceptably mitigated. We do this technology qualification theme based off of things that we wanted to qualify within. So safe operation, wireline compatible, control the tool, the ignition, the reaction, create a permanent barrier, and then somehow verify that barrier did in fact do what it was set to do. We try to follow within these subsections, if you will, specifications set out by North Standard and NACE International and so on. The next couple of slides that we'll jump into here will particularly focus on the permanent barrier subsection, if you will, and more specifically within that, the seal, the corrosion life expectancy, and the potential for fractures that were tested. So moving into the next slide to discuss seal potential. In this slide here, the barrier on the right-hand side of the slide was, again, that image you saw earlier, cut open 180 degrees. From that full-scale test sample, a section of that highlighted in the box D was taken. Excuse me. Then from that sample D, we picked 3 other areas located A, B, and C to take an understanding of how this product actually permeates and gets into the caprock, if in fact it does do that. So each of these 3 slides, A, B, and C, are showing those various areas and identify that our product can permeate or flow into very, very tiny cracks down to the size of 1 micron or 1,000th of a millimeter. Relating to the previous slide, explaining the difference about bismuth melting and production. The viscosity of liquid bismuth will decrease as temperatures increase, which does allow it to in fact permeate or flow into these very tight small spaces and provide 360-degree rock-to-rock coverage of that surrounding caprock. In other words, Interwell's high temp thermite reaction, it enables the bismuth to permeate or flow even further into the caprock compared to that of a melting application. Our heat, again at 3,500 degrees Celsius, is why we're able to do that. It's also important to note that as a result of this reaction, what we do is remove those wellbore elements, those casings, cement, mud, fluids, to create that void space, which is what we actually do by placing, where we will actually place our barrier is in that void space once it's removed. These wellbore components do not have a negative influence on our ability to get to the borehole interface. Next slide, we'll talk about the corrosion potential or life expectancy of the barrier itself. So for this test, and again, as a part of our technology qualification, we sourced out a third-party organization to conduct this testing. Syntef was selected for this process itself. They were utilized to provide testing to test at 3, 6, and 12-month corrosion tests. They were conducted in a corrosive replenished system, 5% CO2, 1% H2S, temperature of 100 degrees Celsius, and 11 bar. I should back up quickly here. Syntef, again, for those of you who aren't familiar with them, they're one of Europe's largest independent research organizations, and they were the ones that conducted laboratory tests of this environment. The result
Hey, Travis,
lastly, yes.
we lost you again for a second there.
Okay.
Just on this rock solid life expectancy slide. So
Okay.
maybe you could back up to where you were talking about the conditions.
Sure, I'll just kind of try to jump in to the middle here, I think is where you might have lost me.
Yep.
So what I was saying is that 3, 6, and 12-month corrosion tests were conducted in a replenished system with 5% CO2, 1% H2S at 100 degrees Celsius and 11 bar pressure. At the end of the 12-month tests, it was determined that there was no visible, measurable corrosion and no failure mode due to corrosion. Syntef's claimed that this barrier, for all intensive purposes, as far as testing is capable of going, can be conducted or deemed as an internal perspective, if you will, an internal everlasting barrier. It won't break down. Making this product suitable for sour gas, CO2 wells, CO2 storage systems, among others. Moving into the formation fracture potential slide. Next slide, please. So one of the common questions that we get asked is, as a result of the heat that we generate, do we create formation fractures at that setting depth? So for this, we again enlisted Syntef to conduct testing, third-party organization to conduct fracture testing. The findings were that fractures can't appropriately be tested in an experimental setting because we simply cannot create the overburden of a natural downhole environment. However, there were no observed fractures of any kind during any test that was conducted. And the conclusion was that test conditions were likely more favorable to create a fracture system. However, again, none were observed. Of the type of possible fractures, the tangential fracture type was the one most likely to occur, as surrounding stress pushing inward into the borehole has less supporting pressure pushing back, causing those initial first layers of the borehole interface to potentially fall into the hole itself as that hole is created. Test samples indicate that the heat effects of our reaction only reach plus or minus 1 inch into the borehole interface. We have core samples cut open that we have investigated this with to provide evidence that you can see the heat effect within that 1 inch of that borehole interface. However, what's removed is essentially replaced by the bismuth alloy that we create due to its low viscosity and ability to flow into. So any kind of pore space in close proximity is filled with the barrier elements, the bismuth alloy, as a result of that reaction. It's also important to note that the mineralogy of the rock does not change as a result of this heat. The heat is the main load on the system and depletes rapidly as you with depth of formation. So as you get further away from the heat source, that pressure is not 3,500 degrees Celsius. It depletes quickly. Next slide, please. So taking all of our operations, from testing into the field, so how can we evaluate the results of our reaction at 3,500 degrees in a downhole environment? Well, we've got some pretty specialized equipment as a result. In Norway, where our R&D lab is located, we have 4 custom-made pressure tanks designed for testing under pressure to simulate wellbore conditions. Every test that we do in half scale or full scale, we manufacture a mock-up of the well elements. including the casing. We cement that inside of a caprock analog. During the test, we're able to run that test, and with a custom-made saw, one of which you can see in the picture here, we're able to immediately after that test evaluate the barrier by cutting it open. We do that one day after the test has in fact occurred. To date, we have run over 800 tests, 600 of them being pressurized. So that 598 total is a P test, is pressurized tests itself. Since the beginning of our technology, again, back in 2012, in 2016, we started field deployments, initial trial field deployments. We did 18 with the first generation tool. And since 2020, we've done 2021, if you will, kind of mixing in COVID, we've done 15 with our generation tool. So the learnings from the first generation tool, thanks to COVID in part, we were able to go back in R&D and fine tune and modify that process and that product to get to our generation tool, which is what we're offering today. Generation 1 only created 2 phases of the barrier, whereas generation 2 creates 3. The third element is the actual bismuth alloy that we create from our reaction. So all of this in the next slide is how we've come to qualify our technology. Obviously, there's far more in-depth steps than what I've documented here, but that for the gist of it, if you will. So in 2014, we received a statement of feasibility from DNV. In 2016, they endorsed the qualification plan. And in January of this year, we received our statement of qualified technology for both our current barrier offering sizes, 4.5 inch and 5.5 inch tool dimensions. So now that we've got our barrier qualified according to DNV, moving into the next slide, we'll kind of discuss a bit of the application of that. So at the beginning of the presentation, I mentioned how our initial objective was to create a barrier to be a deep set reservoir isolation barrier in an offshore environment. That conceptual idea went to Canada and to an onshore environment to be utilized and tested to verify that barrier. The last component was to verify the barrier. So we selected casing, surface casing vent flow or sustained casing wellbore pressure well bores to do that testing itself. So if you just hit the space bar there, it should start to show. So a plug barrier essentially creates one barrier inside of casing, doesn't do anything to address any kind of flow path potential in the annular space. The annular repair barrier, again, creates that inside casing barrier. Generally perforated casing or communication point is established to access that annular space where a product is then squeezed into. Cement squeeze remediation techniques would typically fall in this category. And lastly, the cross-sectional barrier, which is what rock solid is. We go into the casing, through the casing, create a reaction that removes that casing barrier, removes all the wellbore elements surrounding it, gets to that borehole interface, and in that void space, we place our bismuth alloy sealing barrier element, made up of 3 phases. The bismuth alloy creates the seal. The sequesters are in the middle, encapsulated by that bismuth alloy, and the top is the anchoring system, the oxide or artificial rock, creating that rock-to-rock bond. All of this creates that 360-degree coverage, removing potential flow paths, creating one single flow path elimination product. So again, in the next slide, sorry, discussing more in the surface casing vent flow, sustained casing pressure wellbore. This image is a generic one, kind of similar to the one shared earlier by Inotech Alberta, just identifying potential flow paths or issues within a borehole itself in a well completion. So understanding what the problem is essentially is how we're able to try to prevent or eliminate that flow of gas or oil, or sorry, liquids from above and below the barrier. Traditional project strategy shortfalls, possible limited remedial products that were currently available to industry, poor placement, poor product performance, or unique challenging wellbore geometry. What we mean by that is in the event that you've got small microannulus or fracture systems channels in your casing that we're trying to access through casing, from inside a casing, and ensure that we're able to get to that flow path in order to place a product there to eliminate that flow tunnel. So we kind of said, well, what if we just remove the issue instead of trying to work with it? So this next slide is a quick animation, and we discussed earlier, we spared you with the sound. So I'll just kind of describe as we hit play here what's going on. So I touched a little bit earlier, our barrier requires a bridge plug set at the setting depth. That is for us to set off of. We will simply lower our tool down, set on top of that. At the bottom portion of our tool, we have a nose cone. Creates a thimble ring and it prevents the liquid bismuth alloy from falling down into the actual fish neck of the bridge plug. Above that, we have an anchoring system, again, holds the tool in place, prevents tool jump during the reaction. Signal is sent from surface down the line and the ignition process is instigated. The reaction removes the casing, evaporates the liquids, evaporates the cement and wellbore elements. Liquid bismuth is then able to flow into, again, tiny little fracture pore spaces down to 1 micron in size. The full reaction takes about 15 to 20 seconds. At the end of the 20 seconds, the reaction has completed, and within 1 hour, you have a functional barrier. Within 24 hours, that barrier in it has rematched the geothermal temperature gradient of the surrounding environment. And at that point, it is a solidified barrier, eliminating the flow path from within the borehole. So that's a little bit of an animation on that. Next slide is just going to show kind of where our second generation wells are. So first off, I have to apologize. This slide is outdated as of the time of this presentation. Recently, we've conducted 2 additional wells. So to date, we have actually conducted 15 field operations within the specifications of our tool. 12 of those deployments are verified, meaning that they're considered verified by Interwell, the operator, as well as the regulator in the region. 2 of the deployments that I just mentioned recently conducted are sitting in monitoring status. These 2 deployments, as well as 1 other, are in that pending verification status. So the other one is currently being monitored as well as part of their the company's long-term monitoring program before they deem success or a failure, if you will. All 15 tools were successfully set on first attempt. We've had no HSE or operational incidents to date with any of our deployments. All of these wells, as you imagine, were nuisance wells for the operator with vent flows. Many of them had many previous remedial attempts conducted prior to the interwell deployment. We do have a case example or case study, if you will, on our website. I encourage anybody to go to interwell.com. Under product solutions, you'll find our 3 divisions, and there is a case study there to describe one of these wells in finer detail. So what's next? In the next slide, what's next for Rock Solid in terms of our timeline? So currently, as I mentioned, we're in an onshore only environment. We are in a single string environment available for 4.5 and 5.5 inch casings. In 2024, about mid-year, we do expect to have our 7-inch solution available to the market, again in a single string onshore environment. We will be conducting this in Canada as well as the United States, and we're evaluating well candidate potential in the Middle East as well. Moving on for the next few years, we are going to start continue our process to getting to an offshore environment, starting with a single string wellbore scenario, eventually working into a dual string scenario and a through tubing string scenario where we can go through tubing and deploy in a casing, or through a restriction and deploy in a larger OD below. All of these things are eventually moving us to that dual string subsea kind of reservoir barrier and offshore barrier system. The 2030 deadline is a target for offshore in Norway specifically. So lastly, last slide here, just to quickly recap, Rock Solid barrier. It removes all the wellbore elements in the cross-sectional area to place in that void space a permanent gas-tight, unpermeable bismuth alloy barrier with a sequestered metal casing in the middle and an oxide or artificial rock, creating that anchor system at the top. We don't try to work with the surrounding environment, cement and things of that nature. We just remove it all in order to get to that borehole interface and plug that entire pathway. It's a targeted thermite-based reaction that again reinstates that caprock integrity. It's a rigless deployment that we deploy off of wireline or E-line specifically. And we as well to ensure that the technology is suited for all relevant applications and as many customers as possible. We are looking for well information or potential field trial candidates from potential customers and customers of current for all future deployment scenarios that we kind of listed in the timeline before. We are working towards getting into larger casing sizes in that 9 5/8 scenario, which is typically what you would find in an offshore environment. It is understandably a process. So it's important to keep in mind that this product is new for all intensive purposes. It's been developed over the last 10 plus years, has been deployed in field trials since 2016 and is now kind of commercially offered to industry with a limited operating window that we are constantly expanding. We aim to do that in a controlled manner, obviously, and get to our goals in time. And that's the end of the presentation. So if there's any questions.
Yeah, thanks, Travis. That was very thorough. So I think you probably answered a lot of the questions people have, but I can start with one. So you, in the diagram you show the length of the bismuth at the bottom and then other components above. What is the length of the barrier? And is bismuth considered the barrier, or is the whole sort of assembly of different materials providing sealing, I guess?
Question. So the length of the barrier is from 1.5 to 1.8 meters in vertical height. Interwell considers the barrier to be all three components. The oxide or artificial rock, if you will, at the top portion actually creates an impermeable barrier as well. That is what we used in Generation 1 tool to create that barrier itself. So it is a barrier as well. But the piece or the component that's in fact creating that gas type barrier type system is in fact the bismuth alloy at the bottom. That bismuth alloy is, in terms of vertical height, anywhere from 12 to 20 inches in height.
Great. Oh, the questions are coming in now. So we have one here from Randall Miller. I've found the bismuth to perform well when reestablishing casing integrity. When you have a very small feed rate, have you seen applications where bismuth is being used when there are small casing leaks? So this might be a little bit outside of what you guys are doing, but I'll let you answer.
We don't essentially address casing leaks unless there's a larger problem, i.e. sustained casing pressure or vent flow. For us to address a casing leak, we would need to deploy in an area that fits within our parameters. So number one parameter that we require is a comparable caprock, so a shale or tight siliciclastic, sandstone, siltstone, mudstone, things of that nature. So if the leak is in fact at a very porous type sandstone interval, as an example, that interval isn't a deployment candidate for us. We could do that, but I'm assuming that with a casing leak, a wellbore access below the depth to remediate might be desired. And again, our barrier is in fact a permanent barrier, so it's creating a new TD in the wellbore.
Sounds good. So we actually have three questions here they're all related, so I'll try to combine them. But so if you need to remediate the deepest source and the attempted remediation doesn't kill the vent flow, and you need to re-enter the well, can the plug be drilled out?
So I will say that to date we have not done a drill out test to answer that yes or no definitively. However, we are working with operators to conduct a drill out test to get that answer for clients. It's kind of a challenging question because what we're aiming to do is to not have to have you drill out that barrier. So deployment depth selection is extremely important, knowing that you're above your source. Again, this barrier eliminates a flow path from within the borehole. So if there's a well flow path or a flow path in the formation or surrounding geology that's going outside of the borehole, then we're not able to eliminate that. So we're not permeating a long distance out like cement will into a perforation in the surrounding area to create a barrier. We're only eliminating the borehole. So I would challenge customers that want, really focused on the ability to drill that out to say, well, we're eliminating, we've put a barrier in your borehole. So if you believe that that barrier does what it's intended to do, then there is no flow from below getting to surface inside of your borehole. So perhaps remediation shallower than that barrier depth is what's necessary. But again, we are going to conduct a drill out test. We can cut the barrier open with a saw. So we do know that it's able to be opened up. So we aim to do that test in Q1 2024 to have that answer yes or no, it can be drilled out. It'll be more of a coring of the barrier than necessarily a complete drill out.
Sounds good. We have a question here from Fred Wasmith. With the thermite reaction running above 3,500 degrees C, do you vaporize the bismuth, or does the well pressure reduce this effect?
It is initially a gas, yes. It quickly will turn to a solid because of that rapid depletion of temperature from the source. So initially it's a vapor that quickly turns to a liquid and then eventually into a solid.
I have a question. So in your experience here in Western Canada, Alberta, BC, and Saskatchewan, you mentioned that the regulators have approved it for non-routine abandonment. You might not have this information, but after a successful long-term monitoring of the well, is that the only operation that's needed then? Like, can you cut and cap those wells?
Yeah, so current requirements require a bridge plug, if that's what you're asking. A bridge plug be set on top of a barrier to, again, pressure test your casing above to make sure there is no other additional integrity issues. Our barrier does not require that step. That step is, in fact, completely separated in that process from what we're in fact doing. So it is, in Alberta specifically, it is still required that you would put a bridge plug and pressure test your casing above, but that bridge plug is not required because of our barrier. So we're not treated like a bridge plug and 8 meters of cement, if you will. We're kind of in a different category because of what we're in fact doing. I hope that answers your question.
Yeah, that's good. We have a question here from Dave Fukumoto. You mentioned the ability to deploy against a tighter clastic. Has this been attempted, or has it been predominantly a shale cap rock?
No, we have deployed. We've deployed in shales. We've deployed in tight sandstones, mudstone, and siltstone to date. So all of our deployments have been in a different depth, a different formation type, different geology type, different casing size. So we're not targeting like one very specific type interval. We in fact want to understand the range of what we can do. So we are also investigating setting in a limestone type system as well.
Excellent. I have, I guess one more question here, kind of from the Canadian perspective, but what are your operations in Canada, and are these 4.5 and 5.5 inch tools here?
Yes, so we do have tools in country. Our process right now is, in terms of personnel, we will fly personnel in from Norway or from Houston, Texas, to deploy the tool. Tools are located in Canada. We are working towards, with the demand support, of course, full-fledged operations, self-sufficient operations in Canada, with personnel and people able to deploy quickly.
Excellent.
Sorry, and 4.5 and 5.5 are available in Canada, yes.
Well, I think that's all the questions we have for you. Thanks, Travis. As I said, that presentation was very enlightening, so appreciate it.
All right. Thank you very much. Appreciate it.
And with that, we can move on to our third presentation, which is Ryan Wilton at SNF. So Ryan, I'll let you take it away.
Good morning, everyone. Yeah, thanks to everyone at Initech Alberta and the CRIM program. We're relatively new to the program, but appreciate the opportunity to discuss our technologies for well remediation and plug and abandonment. Go next slide, please. So just an introduction to who SNF is. We're a water science company. We largest polyacrylamide production. I see there just sales just over 4 billion. The majority of our products that we use in oil and gas will be related to flocculation, viscosity modification for enhanced oil recovery, products for drag reduction. So we're trying to increase water transport, decrease pump pressures, that kind of thing. And as a result of this, we have products that we use for conformance, reservoir conformance, water shutoff, water control, essentially. And so these products we think we can extend into a remediation plug and abandonment application. Next slide, please. Just in general, how our products are manufactured. So they're derived from propylene. Essentially, we're using acrylonitrile, acrylic acid to create copolymers of acrylamide and acrylic acid. So we create a liquid process initially, form a gel that gets granulated down and sieved to a specific size, and then we get a randomized charged product. So we've got a carboxylic acid randomly distributed, and for our MeriSeal applications, this would be very low charge, and these would be low molecular weight polymers cross-linked with chrome. Next slide, please. So this just describes some of the problems that we're dealing with. So as I mentioned, most of our applications with MeriSeal are going to be for reservoir conformance. These are injection side problems, whether they're fractures, high perm voids. We have got maybe viscous fingering, but we're trying to fill and improve the sweep efficiency from the injection side. But obviously from the producer side, we have problems as well. This could be coning into the well, casing leaks or flow behind the pipe. Maybe we've drilled into an open water zone or fracked into an open water zone, and now we want to stifle that water production. Or in the more extreme case, we want to actually plug and abandon the well. So some of our like the initial technology MeriSeal, we're looking at, can we potentially treat the well first and bring it back on production, and if not, then fully abandonment. There may be some opportunities there where wells are prematurely abandoned without fully extracting the oil resource. Next slide, please. So in terms of how the MeriSeal gel performs or is formed, so as mentioned, we've got roughly 5% hydrolyzed polyacrylamide, easy to dissolve at any field brine. Concentrations used might be between 5 and 50,000 ppm, again depending on how the strength and the quickness of the gelling that we want. For the most part, we're using chrome 3 either in acetate or chloride form, again depending on the speed of the reaction. But in the schematic here, you've got two polymer molecules. Through that carboxylic acid functional group, we can get chromium coordination. Once you have a certain number of coordinations formed, you get more and more rigid structure. So we move from a very flowable gellant into a more rigid gel structure that can resist water flow. Next slide, please. Just in terms of the typical properties and behavior for these MeriSeal polymer gels, another product we have is a market gel, which is a higher molecular weight polymer. So we use our AN907 polymer versus the AB55. The AB55 forms a more robust gel. So you see in the schematic or the picture in the bottom right corner, the MeriSeal forms a ringing gel, so it's very little surface deformation. And the initial viscosities on these, if we look at the green curve on the bulk viscosities, at concentrations down at 15,000, we're under 10 centipoise. So we're getting to very water-like type initial viscosities. So these can easily flow into fractures, fissures, flow behind pipe, etc. And we can modify the chromium content to change the gel structure. We can also increase the strength, and this is what we're working on right now, is looking at additives, microcements, sands, fibers, and this might be only needed to be added to the very last volume that's injected. So the previous gel injected may be strong enough, and then we just cap it above the perforations with something that's a little more rigid with some stand structure. In the top right, though, you see this particular polymer system. Excuse me. Initially, the viscosity is relatively constant, and then after a certain time, coordinations, we see the viscosity basically go off scale. Next slide, please. So just in terms of the difference, an injection side treatment, we're bullheading the gel into these features that exist. This is just showing a schematic for a horizontal system. Again, we're playing off the initial viscosity and the gel kinetics to allow us to have in-depth placement, starting with a low viscosity gel. A lot of times we're seeing breakthroughs from the injection well, the producer well, on the order of hours. So we need varying grades of gel to fill that. Conversely, from a production side, and this is showing a producer horizontal pair, but the concept would be the same for trying to plug or abandon this. In this particular application, we would do a sort of a protectant of the wellbore first, and then follow in with our Meraseal gel, again playing on viscosity to enter in these features that are strongly connected to the producer. There's a shut-in period, and then in this case, we want to turn the well back on. In terms of a plug-in abandonment case, we'd want to have a full seal on this, at least in the vertical section. Next slide, please. So the first part of that talk was dealing more so with our flexible gels, again, something that starts liquid, forms a solid. We also have a new product that's relatively new. It's had some application in Australia and Europe, but not a lot of application yet in Canada. So this would be sort of a cement replacement. Again, we're looking to permanently isolate and control the zone, but still create some infiltration into the fractures and create a seal between the rock and the casing. So again, cement replacement. There's maybe some impacts on porosity and gas leakage through the system that we can improve upon versus cement. And again, we're looking for a permanent waterproof seal that allows us to abandon this well without using cement. Next slide, please. So in terms of how the flow set material, just the Meraseal, going back to that real quick, is a two-component system. As I mentioned, you got your polymer and your crosslinker. For the flow set gel, there again, it's ultimately a two-component system, but the solutions can be pre-mixed for the most part. So we have a flow set gel 500, which is our polymer or monomer resin that is sort of the main ingredient. And then we have a triethanolamine. This is basically the activator. So those two would be in one separate solution. And then in the second solution, which is a free water phase, basically we have sodium persulfate added in, which is a catalyst reaction. And then if we want to delay the reaction further, we can add in other agents like iron sulfide heptahydrate that will slow the reaction down. So these two solutions are then mixed together in different ratios. The ratios that we find had the most interesting gel properties were a 1-to-1, 1-to-2, or 2-to-1. So these are combined, and then based on some ratio of these components, we can get different gel times. For the most part, we've looked at lower temperature applications, 30 Celsius, seem to get pretty good gels there, although once we get into 50 Celsius and above, the reaction's quite rapid. So we're looking at ways to extend that gel time out for 50 C conditions. But the Meraseal can potentially work quite well at the higher temperatures. So maybe between the two systems, we can hit that temperature range. Then at the end of the gel formation, we cut a chunk out, 1 millimeter slice, and we use an Anton-Par rheometer with a serrated cone plate geometry to get some elastic moduli data off of these formed gels. Next slide, please. So mention you got the part A added together. Sometime we get a gel formation. What I want you to look at here is just a little schematic at the bottom. Of course, it took a few years ago. And it just discusses it, puts it in perspective of cheese actually. So if your brie cheese has very soft elastic modulus, 1 kilopascal, all the way to Parmesan, which has a harder elastic moduli, maybe 1,000 kilopascals. That's sort of our reference in terms of what we're looking at for the flow set. So I think there's a short video now that just shows this reaction now in actual time. Yeah. So this just shows the initial components. So we've got our tea product being added to the monomer resin. Just a quick mixture of those. And then the second part B solution, we've got our MPS being added into our water. That's rapidly dissolves as well. So essentially now we're coming to a two component system that will be added together and form gel. This is all in more or less real time. So this system would be developed to form really quickly. So these are both quite liquid still at this point. So you can see those last few bubbles disappear. This is over the course of maybe 30 seconds to a minute. Viscosity's maybe building a bit there. Not done a lot of flow behavior testing on this, but you can see at this point the reaction has been complete. We've got a fairly rigid material left over that we think can provide a pretty good waterproof seal for these types of applications. I think he dumps it out here at the end just to show. Yeah. So it more or less takes the shape of that container, which we feel could flow into fractures and around the surrounding wellbore. Next slide, please. So this just shows some of the initial testing that we did at 30 degrees Celsius at 1-to-1 ratio of the two components and 1-to-2 ratio of the two solutions. Out of this initial data, just focusing on gel time for the most part, we see maybe 8 potential flow set systems. So there's 1, 2, 3, about 4 from the 1-to-1 ratio and 4 that we feel in the 1-to-2 ratio. You can see the gel times range from 112 minutes, roughly 2 hours, up to about 11 hours, 735 minutes there. So pretty reasonable range in terms of time to not only mix, but get it down to the bottom of the wellbore, possibly recirculate back up the backside of the annulus. And we see G prime values that are anywhere from 6 to 16 times what we'd expect from Parmesan cheese. So this stuff, again, if we can control the reaction and have experienced deployment on site, we feel that this could be a good material. We have a lot of experience injecting MaroSeal compositions. So again, our experience on that side of it could be lent towards the application of this. Next slide just shows the 50 degrees Celsius. So again, we can get rapid gel formation at 50 C less than an hour. But again, if we push the system too much to try to delay it, or even using different delaying agents, we run the risk of pushing it into an area where we don't form gel at all. So the higher temperatures above 50 Celsius may be a temporary limitation of the system until we figure out ultimate compositions. These also have micro cements added, so again, we're looking for more rigidity, but those components will also accelerate the reaction. So not quite there yet with the higher temperature applications. Next slide, please. This is showing some compressive strength data that we've done through a third party and post-treatment permeability. So you can see flow set by itself, only about 1800 kPa for compressive strength. Cement by itself might be in that 24 MPa territory. From the initial testing we've done with microsets and flow set gels, we can increase that strength on the order to more of what we see with cements, with having that additional flexibility to place from a surface application. In terms of the permeability, we can see whether we're using Flowset Gel 500 with and without micro cements. We're into the sub 1 microdarcy permeability, or down into the 60 nanodarcy territory when we have micro cements added. So we feel like that's a pretty good gas permeability to be working off of. Last slide, just summary. So again, some of these applications, we might be able to use a flexible MeriSeal gel technology to see whether that well truly needs to be abandoned. This might be a quick one day treatment, shut it in, put it back on production. If no more oil production occurs, then we know, okay, it's ready for abandonment. Whether that's with a MeriSeal system, with the final volume having some additives to increase the compressive strength above the perfs, which testing's ongoing. Or on the Flowset gel technology, where we form really strong gels, more so just for a plug and abandonment type application. As I mentioned, we're doing ongoing testing there, and would welcome any additional questions from the potential customers on additional testing that we can do to make this a viable technology. With that, I will end my talk and entertain any questions the audience might have. Thank you.
Yeah, well, thanks, Ryan. Very interesting, and yeah, I really enjoyed that video because it's always nice to see it in action. I know we have several chemists on the call, so hopefully we get some technical questions from them that I can attempt to relay. But we have a few others coming in. One here from Larry Friedman. If the product is placed in the wrong spot, can you run a chemical to break it?
Yeah, the MeriSeal polymers and gels, we've had success degrading those with bleach or peroxide solutions. Usually within a 1 or 2 day soak, that will start to be degraded.
We have a question here from Tiffany Lowe. If used and it flows into formation rock fissures, will this product exceed the fracture gradient? And that might relate to a question I have in shrinkage or expansion. Does the product shrink or expand?
We don't see any shrinkage or expansion when in like hydraulic conditions. Obviously, if this was left with the lid open to atmosphere, over time you might see some shrinkage that way. In terms of fracture pressure, the MeriSeal is, like I said, we can tune that quite accurately so that as we start to encounter pressure, we can sort of let off the system, or we start with something that's a little bit more mobile that builds slowly, and then finish with a stronger gel when we're trying to finish off that last meter or so above the perforations. But yeah, the Flowset system is not as ideal for placing deeper into the reservoir unless we can get the longer term gel kinetics.
One here from Cam Geddes. How much would a 1 to 2 Flowset gel cost relative to 100% resin?
Good question. Don't have a lot of comparative pricing yet, but I mean we're more or less talking small volumes. I don't have that pricing for Flowset, but for MeriSeal, something that would require 5 to 10 cubes at most. I mean, we're talking probably in that 30,000 territory US.
Okay. One from Catch a Student. How sensitive are the gels towards pH variations, especially acidic conditions?
Yeah, like in acidic conditions, you would have hydrolysis of the polymer. So we might see the hydrolysis increase. But again, if the gelation happens initially and it's fast enough, I don't know if that reaction will impact the gelation. The crosslinkers themselves are slightly acidic as well. So yeah, we haven't done exact testing on this stuff in these higher pH conditions. These would be more in this between the 6 to 8 pH range.
Thank you. One from Tiffany Lowe. How will water flow within the wellbore affect the product setting?
So both of these materials would displace whatever's in the wellbore. So we'd be pushing that stuff back in or up the annulus, depending on whether it's a P&A or a casing vent type application. But we'd be looking to displace that material and just leave our gel system in the wellbore. And again, some of that can be played upon, by increasing the initial viscosity. We can tune that on the MaeriSeal side.
One here from Trevor Lescu, and it's kind of along the same line. So we had previous ones about pH and water in the wellbore, but there's here, how about salinity of the initial wellbore? Does that affect the setting, or does it have to be circulated over to fresh water?
No, the MaeriSeal system will work in whatever salinities. It's low enough hydrolysis, low enough molecular weight that it's not impacted that much by salinity. The flow set system we have not tested in the presence of salinity. I can't comment on that, on how it would impact that gel system. Again, conceivably that would be displaced, and just the flow set system left in the wellbore.
Great. And one here from Fred Wadsmith. Have you tested the longevity of these gels at moderate temperatures, say on the order of years, and how do they react in the presence of CO2 and H2S?
Yeah, the MaeriSeal products, it's been around for a long time. We do have samples of that years and longer, as long as they're again sealed, they seem to hold their structure. The flow set technology, I don't know if we have longer term data on that, but that's something that sort of we were hoping to get out of this consortium, is what other testing do we have to do that is of interest to our customers within this consortium, that and it sounds like pH, H2S, CO2 impact on especially on the flow set, the kind of data that we don't have, that we need to follow up on. But MaeriSeal seems to be fairly robust to those other three conditions. We've done injections in oil fields that have H2S present with success on the injection side, so I don't see it being a problem on the producer side.
Cool, good to know. Well, it looks like that concludes our questions. So I'd like to say thanks again, Ryan. Very interesting and good talk.
Thank you.
And with that, we'll have our final presentation of today with Mike McDonald from PQ Corp. Mike,
thanks, Johnson. Next slide, please. Yeah, I'm going to go over a few different things, starting with who we are, and then I'm going to present a couple tools we have in the toolbox, alkali silicates, and then geopolymers and how silicates are used to make these geopolymers, and then into the field trials. Next slide. A little bit about PQ, very old company, 200 years, got our start making soaps. And then in 1850s, we started making sodium silicate. And from there, we've grown to be the largest producer of silicate and silicate derivatives. And we serviced every major country using different oil field applications. Next slide. As far as tool and toolbox goes, very, very old technology. First patent on the use of silicates is back in 1922. We're seeing a bit of a resurgence towards silicate-based technology, and there's a lot of reasons for that. It's a solids-free technology. If you look over on the right, that's the silicate molecule in its most simplest form. So we've taken silica, reacted with an alkali, soda ash, and then dissolved it. So that would be the monomer, and we also would have in solution dimers, trimers, oligomers of that silica monomer. As you can imagine, a product based on sand and soda ash has excellent HS&E characteristics, so it is allowed to be used above the base of groundwater. As far as viscosity goes, the picture on the bottom, you have what's called a 3.2 ratio. That would mean for every 3.2 pounds of sand, there'd be 1 pound of soda ash. As is, that's about 180 centipoise. cut 1-to-1 with water, it goes down to about 20 centipoise, and that's at room temperature. So running a 50% solution, you're pumping a very small molecular weight species with a very low viscosity. So very easy to pump in place. Upon setting, it has excellent chemical resistance, very good mechanical strength, and we can formulate over a wide range of problems depending on what's required. And then the other benefit of running with silicates is it offers excellent corrosion protection. And as far as cost goes, it's very, very effective. Next slide. Very old chemical, but having said that, there have been some new developments over the last few years. Some of the tried and true setting agents still used, very effective, but new setting agents have been developed. There's two ways to set sodium silicate. One is to polymerize it to make a silicate gel, or to react it with a metal to make a metal silicate, like a calcium silicate, a borosilicate, alumina silicate. Less to do with silicate chemistry, but the placement methods have improved, and that also helps with the placement of silicate. And over the last few years, PQ has developed a couple new types of silicate. So one being a low alkali sodium silicate. So this product would be in between a sodium silicate and colloidal silica, and capturing the benefits of both products, but cost-wise being more in line with the sodium silicate. The other product that's being used in the oil field and other applications is we've added an aluminum end group to our liquid silicate. So it still looks like regular sodium silicate, so visually be no difference, but it has an aluminum end group. So it could be visualized as like a liquid zeolite or even a liquid geopolymer. Next slide. The other technology I'm going to talk about is geopolymers / alkali activated materials. I'm not going to go too much into the chemistry. It's very well described in the literature. Just on one petro, there's 381 SPE papers and counting. Geopolymers in simple terms is aluminosilicate amorphous, usually a fly ash, a metakaolin, or a tailing material. Put into a highly alkaline environment, typically sodium hydroxide or sodium silicate. The oxides become hydroxides, and they can cross-link to form aluminate silica linkages. The other thing that sometimes get blended in with geopolymers are alkali activated materials or pozzolans. So these are where the silicas become activated and can react with calcium and form calcium silicate hydrates. And this would be materials like slag or pumice. Next slide. Going through the SPE literature, these are the commonly touted benefits of geopolymers versus Portland cement: better durability, better adhesion to casing, tolerant to oil contamination. It has been demonstrated to show self-healing properties, improved tensile strength, so less brittle, less prone to shrinkage, and then a much lower CO2 footprint. So roughly 1/3 the CO2 footprint of Portland cement. Because of these characteristics, they become excellent candidates for plug-in abandonment, as well as for remediation applications. Next slide. They are with some challenges, and these are the most common challenges associated with these geopolymers or alkali activated materials. Dependent on the source of aluminosilicate, so fly ash is varied depending on where it's burned, how it's burned. Likewise, with blast furnace slag, variability between source. The need for high alkalinity. There has been a lot of improvement to make it more user-friendly versus Portland cement, but that was definitely one of the criticisms of geopolymers in the early days. Usually they're higher costs than Portland cement. As I'll show in some of the case histories, they can be less costly. The other challenges are lack of admixtures and regulatory acceptance. Next slide. Why we're involved or interested is the need for an alkali. Alkali silicates are one of the preferred forms versus, say, caustic, and there's a few reasons for that. We manufacture a wide range of sodium and potassium silicates, and we can control the alkalinity based on the ratio of silica to alkali. And because of that, you can customize it to whatever your aluminosilicate source is. And then the silicate anion acts as a cross-linking agent within the geopolymer to impart further strength. So this gives a lot more flexibility over, say, sodium hydroxide or potassium hydroxide. And then we make our products in various forms. So liquids, as shown on the right, and then spray-dried products. So the GD would be a spray-dried sodium silicate. Actually, it's spray-dried of the product to the right of it. The K-Solve 16 is a spray-dried potassium silicate. And those from a cementing background, our metasilicates are also a good activator for alkali active materials and geopolymers. One of the benefits of sodium silicate in powder form versus, let's say, caustic in a powder or flake or prill form is it's less prone to hygroscopic pickup of water. Some of the studies we've run looking at, and this is on the construction side, that geopolymers, even when they're well bagged, if they're alkali activated by caustic, they tend to pick up moisture over time and lose their reactivity. And this is much less dramatic using a spray-dried silicate or a metasilicate. Next slide, please. I think we've seen the figure on the right quite a bit, so I'll gloss over that. Just lots of ways for gas to get out of the well. The fractures tend to be very, very small, and this is where we see a good fit for sodium silicate for blocking gas migration or surface case vent flows. A lot of regulators require this. And over the years, lots of different systems have been developed for the placement of sodium silicate. Silicate plays very well with cement. So if they come in contact, the cement will set up the silicate. So one of a tried and true method is to pump a silicate solution followed by spacer, then cement. So the silicate leading into the very fine fractures, high perm zones, followed by the cement. And when the cement does come in contact, it sets up. The other option is to pump the silicate with a setting agent. So in the case of making a silicate gel, an acid generating material would be mixed in with the silicate. Set times could be range from, well, it could be instantaneous to several hours, if not a day. And the other option, you know, questions about like CO2, H2S, that would be the other way to set it up. So if there was CO2 coming into the well, pumping the silicate in, eventually the CO2 would overcome the buffering capacity of the silicate and you'd form a silicate gel. So you would not need a setting agent in that case. Likewise, if the water was high in calcium, you'd pump it into that and it would form a calcium silicate upon contact. Next slide. A few different options, and these are from different field trials in Canada and the US. A lot of times silicate is pumped as is. So to the top right, that's a 3.2 ratio sodium silicate, diluted 1:1, being pumped in for a vent flow in northern Alberta. To the right, that's a sodium silicate. In this case, excuse me, a setting agent was combined with the sodium silicate to get the desired set time, and that would be the 4.5 ratio, so the low sodium product. And then the bottom, that's West Texas. They were using the aluminum modified sodium silicate for placing and casing repair. A few different methods. You know, chemical injection pumps, so you're seeing that in the pictures. Other ways we've seen silicate placed is put in the casing, and these would be for low leaks, so like thread leaks, casing leaks, so very minimal flow pass, and to put a nitrogen tank and pressure up the silicate in the casing and just have it slowly squeeze in. So that's been done a few different times quite successfully. Also seen silicate usually with the cement pumped and then spacer, and then followed by the cement. The other option for placing silicate, and this has been documented and shown to be highly successful, is to section mill in a silicate solution. So you're generating fines, that creates a matrix, and then that helps seal the pathways and imparts strength. Next slide. So I talked a little bit about silicate as is. Now I'm going to get into the geopolymer technology. We're not a pumping company, but we have collaborated quite a bit with academia, aluminum silicate suppliers, service companies, as well as operators to varying degrees to help develop and promote geopolymer technology. So this is a bit of a summary of that work. Plug-in embedment being the ultimate goal as a material, but as a pathway to get there, people are looking at it for conformance and cement remediation applications. And the target areas are where the material properties of Portland cement are known to be deficient. So these would be areas where there's high levels of CO2, high temperature, so thermal degradation. And then from a cost point of view, if you look at microfine cement, it's difficult to work with, and a cost point, depending on the fineness of the microfine, it'd be like 5 to 10 excuse me, X more expensive than Portland cement. So at those price points, geopolymers or alkali activated materials look very, very attractive in comparison to, say, a microfine cement. And then the other thing that we've seen is regional materials. So whatever the local aluminum silicate source is, so be it in the US, whatever the fly ash source is for that region, to formulate around that, or if there's another particular source of aluminum silicate to form around that material. Next slide. What I'm going to go over is West Texas. We were, had a pretty big role in this this project. There was a highly motivated operator that had their own service equipment and were motivated to try new technology. So what they would like to do was come up with an alkali active material specifically for their wells, which were lower temperature. And the types of repair they were targeting were sealing fractures, casing repair, and water shutoff. Based on this, there was a lot of other operators with similar type wells, and then it would be easy enough to adjust for medium to higher temperature wells based on learnings from the lower temperature. In some ways, medium temperature would be easier because the higher temperatures allow for easier activation of the geopolymers. So it gives a little more formulation choices by having some temperature applied. And learnings could easily apply to other reasons. And success here would also provide a pathway for use as a P&A material. Next slide. What was outlined by this operator, which would be common for a lot of other operators, was minimal preparation on location. So I just add water type product being ideal. The preference was for longer thickening times, so 5 to 6 hours at 110 F. The idea was this would allow deeper placement in the wellbore. Higher tensile strength and a smaller particle size versus your typical Portland cement. And this would be things like casing repair, pinhole leaks, and microfractures. And ideally, it'd be similar or lower cost. And the other message was to make it look and feel as much like cement as possible. Next slide. Experimental, there was a lot of work done. The basis of the work was came out of the University of Texas. They had a joint industry product, CODA. It was looking at a few different things, including coming up with alternative materials, specifically geopolymers for plug-in abandonment. So theory, formulation, development, test methods have been well detailed. So that was the basis for the formulation. From there, it was modified to suit the needs of the operator as well as the local source of fly ash. The way the thickening times were controlled was by the type and amount of silicate. So whether it was sodium silicate or potassium silicate and the ratio or how alkali the silicate was. The other dials that could be turned were the amount of water. So water works as a retarder. Now the downside with too much water is it decreases the compressive strength. So there's a bit of play off between having desired viscosity, thickening times, and maintaining compressive strength. We've looked at admixtures. A couple products showed some potential retarding, but we found that we could get the desired set times just by choosing the correct activator and having the desired water level. Next slide. We wanted to vet this as an alternative to microfine. So this was done using plexiglass with metal shims. The gap between the plexiglass was 100 micron, and then Portland cement was squeezed in, and then it was followed up by the formulation that was developed for the operator. What we found with the squeezing in was it took 25% less pressure, and it went 2 times further. So based on this, it helped prove out that it should go further deeper into the formation. And this was also confirmation theory. If you look at most aluminum silicate sources, fly ashes, it'd be half the size of a typical Portland cement. And as it is mixed into the alkali, the silicate solution, it goes to a smaller particle size as it dissolves. Next slide. No shortage of candidate wells. The first one was a well that had started to produce 100% water. There was good diagnostics on the well, so the operator knew there was microfractures as a source. It was on vacuum. Treatment volume wasn't overly big, 26 barrels, so it was felt like it would be a good first candidate for this system. Next slide. The cost of the raw material was a bit more than a Portland cement. Where the savings was instead of using a pump truck, an acid truck was used for mixing it. So the operator had a mixed tank. The way the product was made was there was a silicate solution. The fly ash was added into the tank. It was recirculated via the acid truck. Once the viscosity got to the desired level, as well as the density, it was then pumped downhole via the acid truck. Next slide. This proved effective, but some learnings. It was safely made on location. Scale up from lab to field showed it could be done. There was some learnings. One of them was thickening time was shorter in the field versus the lab, and that related back to exotherm. And then the acid truck was a lower cost option, and the operator did see some reduction in water. Next slide. There was enough success that work continued. System was changed a bit, so now everything was pre-blended in powdered form. The job was small. This was going to be the first job, a casing leak. He had his own cement mixer, so roughly a 1-yard cement mixer. Materials could be blended in the mixer and then pumped within about a 10-minute frame. The first time it was attempted was in his yard. So once it was made, it was poured into a pothole. So over a course of a year, with a lot of trucks driving on top of it, visually, we could follow how it looked over time and exposure to the elements. Not that that's what was happening downhole, but it did allow for a visual observation of what was going on and how durable the material was over exposure to the elements. And well over a year later, it's still standing up strong. Next slide. So after that, it moved to this trial and others. In this case, the well was producing 100% water. It had been treated with a polymer-based system, so the operator was thinking to try to near wellbore pump in this material. So once again, want something that was very fine, that could be squeezed in. Small batch sizes, so it was run 3 batches made and then pumped using a portable triplex. In front of it, there was no spacer, and then it was displaced with 25 barrels of produced water. There was an increase in pressure as we're pumping, so we noticed that it was blocking off as it was going. And the operator did see a reduction in water. Next slide. Some of the conclusions, starting with alkali silicates by themselves, very long history of successful use in remediation. The alkali activated / GM polymers are showing as promising material to replace cement. Material can be prepared using lower cost and really available mixing equipment. Alkali backed material shows promise as an alternative to microfine cement. And the continued use of this material will increase comfort of service company and operators and allow for its use as a plug and abandonment material. And that concludes my presentation. Questions?
Thanks for that, Mike. It's interesting how variable the chemistry can be, which I guess maybe a pro and con, but can vary it to get what you need. I guess I have a question along those lines. I've heard before that one potential issue with geothermals is just the variability of the reactants when they're sourced from various places over the globe, which you mentioned. How is that dealt with? Is there a way to condition those reactants so that you have the same chemistry, or is it handled with different ratios and additives?
Yeah, good question, Jonathan. I think there's 2 approaches. Looking at, say, the mill certs of, let's say, fly ash in the U.S., they tend to be consistent. So that's where I think there are regional formulations. So if there is a source of fly ash that's in your area, it's formulated to that product. Likewise, tailings or slag tend to be consistent as long as they come from the same supply. To get around, let's say, something for everywhere, something that we're seeing on the civil side is it's almost like blended scotch. You take a few different sources of aluminum silicate, do the analysis on it, blend it together, and then you come up with a consistent product. So that's the other workaround is to blend different aluminum silicate sources to come up with a consistent final product. So we're seeing both pathways taken.
Okay.
Yeah, and I think both address that issue of the variability, because I think that's one thing that has been noted in the past that some very promising formulations, let's say they're based on fly ash, or tried with a different fly ash, and thickening times are way different, compressive strength are way different. So it really has to do with the oxide contents, particle size, crystallinity of your aluminum silicate source.
I could ask one more question, and it's, I guess, a little
Sure.
bit out of the scope of this webinar, but have geopolymers been suggested or tried for primary cementing?
I believe so. I think the focus has been, the low-hanging fruit really has been like water shut-off and cement remediation, where you don't need the regulatory approval.
Yeah, that makes sense. Oh, we have a question here from Trevor Leskew. Has this been tested in heavy oil wells where aluminum silicates are present in the sand and the associated produced water? If so, what were the results?
Yeah, good question. I think silicate by itself has been used for surface case vent flow and gas migration and some water shutoff. But as I said, I know we've supplied in the area. Typically, if we don't hear anything, it means things have gone well. So, but I don't have details.
Yeah, that's understandable, and that's, I guess, some of what we're trying to do with the joint industry project that Innotek's leading is close that gap a little bit so that the material producers receive that information on what's working and what's not. I don't see any other questions coming in, so what I will do now is just open it up for all presenters. Sometimes there's other questions that people have thought of, so feel free to ask those now, including any more for Mike here. You can also feel free to ask any questions to Innotek if you like. We do have one comment. It says, great presentations, everyone, on a very relevant topics. Many thanks. Well, I'll second that sentiment, and maybe we'll wrap up here if you want to go to the next slide, please. If we have one more slide. Yes. So yes, I'd like just to say thanks to our presenters and our audience. Great questions and very informative all around. As I said, Innotek has been conducting several of these webinars over the last several years as things continue to change and develop. So this is the last one planned for 2023, but I'm sure we'll have additional sessions in the new year. So keep an eye on our social media. And if you're on the invite list or the attendee list for this webinar, you'll be included in future announcements as well. So with that, I'd also like to say thanks to Sticks and Stones in Edmonton, who helped immensely with all of the background coordination of this webinar, and Innotek's communication department, who are instrumental in setting up and coordinating all this as well. So really appreciate your help to all of you. And with that, I think we'll adjourn, and thanks again.